Good morning. I hope you had some nice Easter holidays. And now let's go on with the quantum imaging again. And today I'm going to talk about not so much the process, but the analysis. And today's topic is uncertainty, statistics, and reproducibility. And actually, I didn't add, but there is also a piece of visualization at the end. And let's see if this one actually is on the right place. So again, so now it works. Okay. So as usually, we have a bunch of modules to load to run this notebook. In particular, what we have new is, well, we have a data set, and Seaborn we have used. Then we have, this is a bunch of extra scripts that I didn't want to put in a notebook, so I just wrote a little extra module for it. Same as this conf map is something that we're going to talk about during the uncertainty part. It's also a piece I wrote, so that is extra loadable module that you can use if you want to use that. Otherwise, nothing particular. A little trick hack: if you have screens with retina screen, then you can get sharp images if you use this little line down here. So it works on this, and there's improvement in the sharpness if you can do that. Books are quite many actually, and the first two we already have seen. Then we have a little bit about statistics, about how to do this hypothesis testing. And finally, there is a book also about graphics, how to divide it and how to work with it. And there is a lot of sites and papers again. And well, to dig deeper if you want to go into these topics. And even more. So there are some videos and further slides. So there's a lot of information that you can expand into this field. It is a large field, which is also, in particular, part is very much overseen. Many people don't even think that you have uncertainties. There's a great hint. So what have we done until now? We have done, first of all, we got our images, we have enhanced them. Then we have tried to get rid of the noise, understanding what the histograms tell us. And from there, doing segmentations based on either the histograms or other methods, labeling components, doing analysis on these components, and then we got some complicated shapes to analyze in different ways. And finally, today we are landed now in understand what actually this information tell us. So we have some motivation to begin with, some scientific goals. Then we have, actually this one is not updated, I realize. I have reshuffled the outline. But anyway, we have uncertainty, statistical methods, reproducibility, and then looking into the data frames I actually did in lecture 2, I think. So that one moved out from this lecture, then giving space to the uncertainty. So this course is about quantitative big imaging, and until now we have talked about imaging, we have talked about quantification in different ways, but until now we haven't talked about big. So it's not only that it's a lot of data. Some people say that big data means that if it fits in a server rack, then it's not big. And others people think, okay, I have 1,000 images, that's big. So it's always is subjective who and what big is. And a little bit also depends on the effort you have to do the analysis. But what it's all about here is not how big the data is, but more about that you are ready to handle more repetitive data sets or data analysis. So we have the 3 V's: volume, velocity, and variety. And that is the important thing. And that puts some requirements on the analysis. So the analysis should be scalable. What works on one image should also produce the same results on many other images. And it should also be easy to customize, so you can, if you realize, oh, I need to do something else for maybe a new data set, it shouldn't be that you have to rewrite 10,000 lines of code to do that analysis, but just take out a little module and then rerun. So today we try to make numbers. We want to actually describe things in our studies, and that is actually what we have done already in our lectures. But now, in this lecture, we are talking about how we can make this information meaningful. And how do we compare results from different samples or groups of samples, and also within each sample type or group, and between the groups to see if there are. And we also not only have to look at how the populations look, but also what is the impact of our analysis. What is the effect of we tuning maybe a filter to some degree? Maybe it's easier to segment, but on the other hand, you may actually lose relevant information, and that you also need to evaluate to know what you're doing. So you really have to do some parameter sweeps, seeing what is the sweet spot where I'm producing reliable results for all data sets. And of course, make sure that your data or your techniques are doing exactly what it's supposed to do. And finally, once you have got all your data in collected in tables, then at some point you probably want to visualize it. Tables is one way, but usually hard to interpret. So what you usually do is you plot your results in some way, and then there are some ideas and rules how you can plot it, making it more accessible to the observer. So let's start. So getting back to our original image, there we got rid of some noise and tried to find the cells. That was lecture 2 till 4. Then we analyzed shapes, then we went into lecture 5, and if the cells were overlapping, we could even separate them, and then we went into 7. And last week we added on with more, 2 weeks ago actually, with some more characterizing metrics and looking at distributions. And now we have at least some samples, and also we have a large number of metrics that we can look at. If you remember this region props, that was a list of, I think, 10 different metrics that we can play with. But the question is, which metric are actually characterizing the effect that we want to see? And then we also, of course, have a large number of parameters to tune. I mean, every step here has some kind of parameter that we need to tune to get the real. Already the filter, oops, that wasn't meant to. The filter already had some tuning parameters. Then the thresholding, we needed to find a threshold in a way and tell the thresholding algorithm. Depends a little bit. Some algorithms doesn't need any parameters, others need a lot of parameters, and so on. So now we need to bring this together in one meaningful workflow. And one thing we want to do in our experiments is to prove something. And there are two things that we want to analyze in our images, and one is correlation and the other is causation. And with correlation, we can do a statistical relationship between different variables, and it's usually quite easy to show. You're just computing a lot of sums, and then you have your correlation coefficients. Causation is a bit more tricky to show, because it shows that there is a consequence of something happening in a sequence. And it can be very difficult to show, and sometimes even impossible to prove, so you have to empirically or prove analytically. So you have to perform a lot of experiments, with populations of different individuals with natural variations. Then finding the causation can be quite tricky. So you have to plan your experiments correspondingly to get that. And the type of experiments you can go for are two types. One is observational and the other one is controlled. The observational, then you can actually explore large data sets and looking for trends. So in principle, someone else recorded or observed a lot of data, whatever that would be. Could be medical data, could be economical data, and then you have just a cloud of data, and then you want to find something out of it. And this kind of analysis is not always hypothesis-driven. It's just that you want to show some trends or something in it. And from this data, it's quite hard to really find any causation. So an example is we have examined 100 people, and the statistic tells blue eyes is on average 10 centimeters taller than the other ones. Okay, that's what we can observe. Or if you bake 100 cakes, then we find a 0.9 correlation between baking time and bubble size. Yeah, possibly. I would see that there are probably other correlations that are more relevant, probably temperature, for example, or what kind of yeast you used. But okay, let's say that the time has to do with the bubbles. Experiment, and that is the type of experiments that we actually mostly do. And here, in a scientific context, here we actually specify our groups that we want to investigate, and we can control what information there is. So usually you have one, say, placebo group, and then you give them different treatments to see what was the effect of these treatments. And here you can actually get some causation. Examples are, we have a batch of 50 mice, and there is some gene which is on those, and the gene is on the other ones, and it seems like the foot size increased by 10%. That is a typical type of example. Also, if we have some metal cast, you can see that the increase of temperature, then you in some metal cast, then you can see that the number of pores, they increase by 10%, and that's also where you really have different classes. One is temperature 0, and the other one you heating it up to more temperature, to higher temperatures, and then you see some differences. And then we come to the turning point here. What is qualitative and quantitative in our analysis? Starting with quantitative, we can look at our images and tell something from the visual feedback, seeing that, well, there is more of something than in the other one, but we can't really put specific numbers on it. We can also compare with expectations. You can see that with one technique you can do this, and then with another technique you can see that there is difference coming out. And also checking what kind of artifacts we see. There's also a quick inspection saying, okay, this one has more ring artifacts than this one. Okay, then that's probably better. And feedback if the shape looks correct. So all these assessments, they actually are good for you during your development. It's a quick assessment. You can say, okay, this segmentation, give me realistic shapes. Great, then I can go on in that direction. Of course, to really prove that it is good, then you have to start doing statistics around it and quantifying. But the first threshold to say reject or continue is easily done with these qualitative assessments. And when we go to quantitative metrics, then we're talking about we can calculate the specific shape. Now we're just saying that it's squared, but we can actually put numbers on it and give a range between different shape characteristics. And then we can also establish some relationship between the parameters that we put to the experiment and the metric that we measure afterwards. And that brings us to the uncertainty, because every measurement has some degree of uncertainty. You can't avoid it. Just a simple thing that you want to measure a distance. You use a caliper. And the caliper has, if it's good, maybe 10 micron uncertainty. But this is the limitation of how well you can measure with that one. If you want to go beyond it, then you need to take another measurement technique. So this is a quite actually quite an entertaining books. That scientific is a body of statements of varying degree of certainty. Some most unsure, some nearly sure, but none absolutely certain. And that's really an interesting claim, and I think that is something you need to keep in mind. Just because you can count your pixels, they are exact. And what we want is to put some error bars, and that actually beyond what the confidence interval gives us, because you can always compute the average, the standard deviation, and from that you can produce some confidence intervals from a statistical point of view. And well, XKCD always have nice cartoons, so I found this one, a guy who doesn't know how to propagate errors, so he put error bars on the error bars, and that infinitely actually converges to some constant if you do it infinitely. And here now I have said uncertainty a lot, and people often say error analysis, and there is a difference between them, because the error is the deviation from an absolute reference, what it really should be. It's easy to get the value, this absolute value, but the idea is if you have some metric reference, so we have actually to go back to the international standard of the metrics if you want to do it, and you can actually measure the error in absolute sense. So you always need a ground truth to get the error. The uncertainty, on the other hand, is more fuzzy. So you have an average value which you measure, and then you have an interval around it, plus minus the uncertainty. And this is illustrated in this figure here, where you can see that the measured value, the absolute truth, and then you can see the uncertainty interval. fully within this interval with your absolute value. Otherwise, you're really far off. And I haven't read the whole thesis yet, but I think the thesis of Christine Gilman is actually really a nice reference if you want to look at uncertainties in images. So what kind of uncertainties are we dealing with? We can split them into two parts. One is a technical part. How good is our metric? How much noise do we have? Image unsharpness coming from the imaging system. Then we come on with effects that you introduce by image processing. And of course, you have some numerical errors that comes from your modeling in the implementation. Could be rounding errors, for example. And a single rounding is not bad, but if you do it, then your error increases. And then we have the field-specific uncertainties. So you may do some model simplifications in your analysis. And of course, you have variations in your population. It's not easy to produce perfect, exact samples. Or if you're working with in medical field, then definitely each patient is an individual, and you have already there a statistical uncertainty in the range. And then we have all different categories of the uncertainties. So we have systematic and random. The systematic ones you get from rounding errors, uncalibrated systems, maybe even from algorithmic choices. And the random part is from variations within the population. Could also be fluctuations in the source. So if you have some illumination source in your imaging system and that one fluctuates, it also gives you some random changes. And on top of that, you have detect the noise on different levels, how the radiation is captured, what the electronics is doing, and so on. And this brings us to this target practicing plot, where we have different cases. We have accuracy on the y-axis and precision on the x-axis. And really bad is when you have both low accuracy and low precision, because then you have really a splat which is off where you should measure. You can see that it's more focused, but it's still not in the target. And then, of course, going towards the higher accuracy or higher precision, then you can see that with low precision, it's still a splat, but it's centered around what you want to measure. And the ideal case is you have both high accuracy and high precision, but sometimes it's not always you can get that. And that can also be translated into statistical terms, and then we're talking about biases and variances instead. So the accuracy is then related to the bias, and the precision is the variance. Did I now say it right? Yeah, I did. I tend to confuse those two myself, actually. And this is actually more interesting when we start doing our analysis, talking in terms of variance and biases. And in our imaging experiments, we have two cases. One is that we count things, and the other one is that we measure things. And for the counting, then we have discrete items that we can count, 1, 2, 3. And we also just have absolute integer values, mostly. I don't think we're talking about fractions of objects. And here the uncertainties are not so obvious. I mean, you have a certain number of pixels, you have a certain number of items. So the uncertainties comes more from the preparation of the data. And an example of the counting is the area of a segmented region. Then when we switch over to the measuring, then we are measuring some physical quantity. And here we definitely have values with uncertainties. And the uncertainties come from noise and uncertainties in the. One example here is that we can determine mixing ratios of different materials with the help of the gray levels in the image. Because here you really have a scale that you can measure along. And when we're talking about uncertainties, it's also good to think about the absolute uncertainty and the relative uncertainty. We can, of course, always say that we can measure something with a uncertainty of 1 millimeter. But that makes a big difference if we measure the distance to the moon or just the diameter of a coin. Because if you look here, you can see that the relative uncertainty with the distance to the moon is pretty good. Whereas if you measure the diameter of a coin, it's 5% uncertainty in it. So you should probably more, if you are comparing things with large differences, it's more reliable to work with the relative uncertainty. It gives you a better picture of the whole thing. And when we measure our things, now in images, we are talking about pixels, we are talking about gray levels, but we want to relate it to something. And here we have to start propagating our uncertainty. And if you just have a function of the measure of a measured value, then the uncertainty is propagated using the derivative of that variable multiplied by the uncertainty of it. If now we have a combination of different components, then it gets more complicated, and instead we have to do the squared sum, the sum of the squared components, and in the end you have a correlation coefficient. And today I'm actually saying that our variables are uncorrelated, so we can skip this part and only work with these two. And now we have some quantities within our imaging experiments. One is the pixel size. How good is our segmentation? Could also in time series experiments, how precise we can measure the time between observations. And then finally we have also uncertainties in the intensity levels. Now I have 3 examples where I want to show how to propagate these errors. So the first one is to determine the pixel size. It's not always certain what pixel size you have. In our experiments, we actually measure the pixel size for every experiment to be sure what we have. So every time we change the focus of the camera, and that gives us a new pixel size. Then next one is a little bit more, involves more components. That's measuring the parameter length. We have actually that one as a property in region props. And finally, using the gray level to measure water volume behind each pixel. So the pixel size is measured through 2 measurements. One is with a caliper, measure how long an object is, and then in the image, measure how many pixels does it take. And then you get the pixel size by object length over pixel distance. And here you work with, we have 2 actually compute the uncertainty of this ratio, which comes exactly how you derive it comes from this tutorial. There's a tutorial doing it, and in this particular case, I don't think I did the derivation in the notebook, but in the notes for the other ones, I have also done the derivation for the uncertainty propagation. We have our measurements, we have a test object. In this case, we have a sharp object, which is very absorbing. So we can measure the distance across here, which is, with a caliper, 20 millimeters with an uncertainty of 0.05 millimeters. I measured the distance between the edges. Can also be done in different ways. Can do it just dragging a measurement line, but in this case, I did it actually by edge detection. So I detected this edge and I detected this edge, and then I did fits between the two and measured the distance between those fitted lines. And the whole workflow to do that is in this tutorial that you have here if you want to look how I did that. And the pixel distance from that procedure gave me these values. So I have 665 about pixels and 0.32 pixels uncertain. That's actually the standard deviation of the. So the equation we need to do is now have pixel size, the uncertainty of pixel size over pixel size is the uncertainty in number of pixels squared plus the uncertainty of the length over the length squared. And computing this, I have a few lines of code where I enter all the values in the table from the page before, and then I compute the pixel size and the relative uncertainty from this equation, which is that one. And then I print it out, and I can see that the pixel size is 43 microns with 0.26% uncertainty, which corresponds to 0.1 microns. So this is the uncertainty we have in our pixels. And that is an important value, because if we now at measurements in segmented images, then we want to measure the area, and the area naturally takes the pixel size as one parameter. Perimeter as well. Also, if you want to measure the distance between 2 points, you need to know the pixel size. And so all these, they actually depend on how well you can determine the pixel size. And one that I don't mention here is actually also, if you do tomography, actually the gray level, the quantitative gray level is actually also related to the pixels. Also, the gray level depends on how well you can determine the pixel size. So let's next measuring meter length. And now is the question first, how are the edge pixels actually defined? And there are several choices, and that can actually deliver biases into how you measure it. And of course, as I said, the pixel size. And the part of how it's segmented is something I'm going to look into pretty soon. First, looking at an edge, how do you extract it? A very easy way to extract the edge is just to take the image, the segmented image, and erode it by some structure element. So if it's a 4-connected or 8-connected structure element, and subtract that from the image. And then you get actually only the perimeter pixels out. Now you measure this perimeter length. And one way is just to count the pixels. Then I got 18 as the length. Another metric would be to look at edges facing the background. So then I would follow this green line. And then I come to 24. Or yet another one is if you do a center line through the pixels, then I get yet another distance, which is 20.5. And the question is, what is the right one? And that depends, again, on how you segmented the images. So it's a chain of effects that you have to count together. And depending on your choices, you can get biases in the true measurement. So that is something you probably have to vary real world The propagation of the uncertainty is we have our edge, which is 18 pixels long. We have our pixel uncertainty, pixel size uncertainty, and here actually the derivation how I came to this is in the notes, so you can look it up if you like. But in principle, it's the uncertainty of the pixel size times the square root of number of pixels. So that gives us the uncertainty in our measured length is half a micron out of these 18 pixels. So this would then be our estimated length of this object. So the length is, I took the 18 pixels times 43 microns, and then I got to this value. And the last example I want to show is how to measure the water volume from gray levels. And that's something we do within neutron imaging, that we do extract images that actually show only the contribution by water. So the gray level in the image correspond to in the images. And that comes from the transmission. Oops, where am I? Here. Area is the pixel size in squared. And then we have some D that comes from the gray level. So our uncertainties are the standard deviation from the transmission. That's some confidence interval. And then, of course, we have the pixel size again. So after some work, I came through that this is actually just a guess. So that's just a number I throw in here now. But anyway, the thickness of water I estimated is 5 and plus minus 10 microns. And then we have the pixel size, which is this value that we had from before. And here we can see that now the pixel size has a greater weight, and that's because of the derivative of the pixel size. And then I have the contribution by the thickness. And together we get some value that under a single pixel we have the volume of 0.09 cubic millimeters and an uncertainty of about 0.5%. So these are the ways how you can propagate your errors in your measurement. And unfortunately, it easily gets much, much more complicated. These were just the simple cases that I showed today. But if you want to have computed for example, the volume, water volume behind the segmented area, then you have to add on the effect of counting pixels. So then you probably would have to multiply it by square root of n as well. And you would have a long sum. Yeah. So and the last thing before the break is also talking about the confidence of our presentation. Already in lecture 2 and later in lecture 4, I talked about confusion matrices, ROC curves, and heat maps. And the problem is that these are only metrics of how good your algorithm is working, not how the specific segmentation is actually doing. This is a part inspired by Peter Moonen's talk at ICTMS back in 2019. And I think he has a paper in preparation for it now. And no, it's actually how good our segmentation was. How confident are we about each segmented pixel? And now we have to go back into looking into the statistics. Assuming we have Gaussian noise, you would get an image like this, just a single class, with some Gaussian probability density function, and that is what we actually going to work with now. When we look at threshold in two images, you have seen that we have, we have the options of true and true positives and negatives, but we also have false positives and negatives, and that depends on how much you have of each, depends on where you set your threshold. It's about to say, if we set a threshold at a certain point, what is confident are we about that pixel value? And as you can see, if we have a value over here, it's not very sure that we do the right thing. And for that, Peter Moonen introduced this way of computing the confidence values. And what we need to do is first finding the Gaussians of our different classes, and that can be done, for example, using something called Gaussian mixture model, which you find in scikit-learn. So in principle, what it's doing, it's identifying the Gaussians you have with their parameters. Then we need to normalize it, so we can do different principles, but I use now peak to 1. So the peak of each Gaussian is equal to 1. You could also do that area under the curve is equal to 1. And I think that probably in the end doesn't make much difference, actually. And from there, we compute some weights. And the weight is just for a given value, gets the probability of that specific value from the Gaussian distribution. Then from there, we can compute the confidence of each class, I. We have the weight, we got it from here, over the sum of all weights. And looking here, again, we have, for example, we have from the orange one, we will have one weight, which is down here. And from the blue one, we have another weight, which is from here. And you can already see that if you come from the orange side, your confidence is quite low. If you come from the blue side, then it's much higher. And here is an example where I do it. I put my threshold and I computed the confidence values for class. But anyway, now as the blue class is class 0 on the lower end, and the orange class is over here on the upper end. And I compute the confidence values based on the weights I get from the blue curve and the weight I get from the red curve. And together we have weight 0 over the sum, gives us these values. And if I come from the left side, I have a low confidence. If I come from the right side, I have a much higher confidence at this threshold point. And this now is something that I want to put into the image, do a segmentation. For that, I have 3 classes that I want to segment with different mu's. Each is has a Gaussian noise with sigma 1. And I also, to make it a little bit uglier, I give it a smooth version of that image before I added the noise. So you can see we have both noisy and unsharp edges. And from there, I can take the image. One more thing. In this example, I didn't apply any segmentation method. I just used the ground truth as the segmented. So ideally, should segment it that image and do analysis based on that. But now I just used this ground truth. And with that, I get compute the confidence images for class 1, class 0, 1, and 2. And you can already see that within each real true class, you have pretty good confidence. But interesting This one actually has good confidence along the edges of reason why that we have the big step between that we have multi-class segmentation, and here in the unsharp edge you partly run into an intermediate class. We combine all these with the help of the mapping from the segmented image. We get the final confidence map, which looks like this. And here you can see that, okay, thanks to the noise, we have some uncertain classifications. When we come to the edge here, it is a bit certain, but our greatest uncertainty is actually around the edge where we have the high valued class to the lowest value class. Confidence curves to the middle here goes up the orange one. So this is a tool how you can see how well you have segmented your actual image. And that's not based on the ground truth, but it's only based on the data itself. And where does this matter? If you have low or high confidence, in high signal-to-noise ratio images, it has the most impact around the edges. So parameter measurements gets more or less uncertain. If you want to compute the tortuosity, can be relevant. Also for network connectivity, because what's happening if you have, for example, porous sample, and you have grains that are touching or not touching, then if they're touching, then you close the path, and then you change your network connectivity. Same for the tortuosity. If you could have a straight line, but it's closed, and you have to take a different line, so it also has an impact on that. And if you want to compute the volume of small items. So if you have very small items, and then they are almost only edge, then it can also have a great impact. For low signal-to-noise ratio, then of course, we have all the high signal-to-noise SNR issues, but then can also come to porosity measurements, volume measurements, and in the end also how you label things. So this is a pretty good feedback on how well you have segmented images, and I think it's worth considering in your analysis. And with that, it's time for break.